Welcome to Brain Vision.
Okay, so we know the inlet velocity can be equal to the inlet volume flow rates divided by the inlet area, which can be expressed as V1 dot over pi times d over 2 squared. So d here is the diameter, which is 10 inches. If we convert to feet, it's about 5 over 6 foot. Since we know 1 foot is 12 inches, and the volume flow rate is given as 450 feet to the power of 3 per minute. So now let's plug in back to the equation to determine the inlet velocity, which is equal to 450 feet to the power 3 per minute, and then divided by pi times 5 over 6 feet over 2 to the power 2. And this will give us the inlet velocity is about 825 feet per minute. So now let's take a look at the second question. So first we need to apply the energy balance equation, which is E dot in equal to E dot out. If we expand it, we have Q dot in plus M dot H1 is equal to M dot H2. Q dot in is the heat, the rate of heat transfer into the air, and M dot here is the mass flow rate of the air, and when H1 is the initial enthalpy for the air, H2 is the final enthalpy for the air. If we do some arrangement here, we have M dot in, Q dot in is equal to M dot times H2 minus H1. And we know H2 minus H1 can be expressed as Cp times T2 minus T1. Cp is the specific heat for the air at a room temperature, and T2 is the final temperature, T1 is the initial temperature. So eventually we have Q dot in is equal to M dot times Cp times T2 minus T1. And we know the mass flow rate can be expressed as the inlet density of air times the inlet volume flow rates. So if we do some arrangement here, we have M dot is equal to P1 times V1 dot over RT1. P1 is the inlet pressure, R is the gas constant for the air, and T1 is the initial temperature. So eventually we have Q dot in is equal to P1 times V1 dot over RT1 times Cp, and then times T2 minus T1. So therefore T2, which is the exit temperature, can be equal to T1 plus Q dot in times R times T1 over P1 times V1 dot times Cp. So we know the inlet pressure is 15 psia. The inlet volume flow rate is 450 feet to the power 3 per minute. And we know the gas constant for the air is about 0.3704 psia times V to the power 3 per pound mass times Rankine. The initial temperature is 50 degrees Fahrenheit. If we convert it to Rankine, it's about 510 Rankine. And we know the rate of heat transfer into the air is 2 British thermal units per second. If we convert to British thermal units per minute, it's about 120 British thermal units per minute. And we know the specific heat of the air at a constant pressure is 0.240 British thermal units per pound mass times rank, degree Fahrenheit. My bad. Oop. So now let's plug in back to the equation. So we have T2 is equal to 50 degree Fahrenheit plus 120 British thermal units per minute times 0.3704 psia times V to the power 3 over pound mass times Rankine, and then times 510 Rankine. The reason why I use 510 Rankine instead of 50 degree Fahrenheit in this case is because it's multiplied by the gas constant, and gas constant has units Rankine here. So in order to match with the gas constant, we need to use the temperature in the Rankine form. So let's keep continuing. So over 15 psia times 450 feet to the power 3 per minute, and then times 0.240 British thermal units per pound mass times degree Fahrenheit. and this will give us the exit temperature, which is T2 here, is about 64 degrees Fahrenheit. And these are the answers for this question.